In this example problem, we're given that there's two forces, force 1 and force 2, that are acting on the hook that's shown below. So it asks us to determine what is the magnitude of force 2 and its coordinate direction angles alpha, beta, and gamma, so that the resultant force Fr acts along the positive y-axis and has a magnitude of 800 newtons. Right. So what I'm going to do here is I'm going to draw our resultant force on our diagram. Alright, and we know that the magnitude of Fr is equal to 800 newtons. Alright. So we know that our resultant force Fr, we know it's equal to force 1 plus force 2. Alright, we know force 1's magnitude, and we're given its three coordinate direction angles, alpha, beta, and gamma. So we can solve for force 2 by saying that force 2 is going to be equal to the resultant force minus force 1. Alright, so in order to do our vector subtraction here, what we need to do is we need to write force 1 and our resultant force in Cartesian form. Okay, so write force 1 and Fr in Cartesian form. Alright, so to do that, what we can do is, force 1, we know its magnitude is going to be equal to 300 newtons. Alright, and we can multiply that magnitude by the unit vector of force 1. Alright, and that'll give us force 1 as a Cartesian vector. So we can write this as being equal to 300 newtons times the cosine of alpha times the unit vector I plus the cosine of beta times the unit vector j times the cosine of gamma times the unit vector k. All right. So from the diagram, we were given that alpha was equal to 45 degrees, beta is from the angle from the y-axis to force 1 is equal to 60 degrees, and then gamma, which is the angle from the z-axis to our force vector, was equal to 120 degrees. All right. So if we multiply 300 by the cosine of 45 degrees and the cosine of 60 degrees and the cosine of 120 degrees, we can get the x, y, and z components of force 1. Right? So force 1 is going to be equal to 300 newtons times the cosine of 45 degrees, which is equal to radical 2 over 2, times I plus the cosine of 300 newtons times the cosine of of 60 degrees, which is equal to 1/2 times the unit vector j plus 300 newtons times the cosine of 120 degrees, which is equal to negative 1/2 k. Alright, so if we just do all this math really quickly, you get 150 newtons times radical 2 times I plus 150 newtons times j plus negative 150 newtons times the unit vector k for force 1. All right. So the last step we're going to do here is we need to write Fr as a Cartesian vector, which is really simple because it goes along the positive y-axis, and we're given its magnitude. So it would just be equal to 0, I, plus 800 newtons, j, plus 0 newtons, k. All right. So then to find F2, we know that F2 is going to be equal to Fr minus force 1. So we're going to subtract our x, y, and z components from force 1. into our resultant force. So if we do that, we get F2 is going to be equal to minus 150 times radical 2 newtons I plus 800 newtons minus 150 newtons, which is equal to 650 newtons times J plus 0 newtons minus negative 150 newtons, which is going to give us 150 newtons K. All right. So once we have force 2 in Cartesian form, we can calculate its magnitude by taking the square root of the sum of all the x, y, and z components squared. So we get minus 150 times radical 2 squared plus 650 squared, 650 newtons squared, plus 150 newtons squared. If we do all that out, we end up getting 700 newtons for the magnitude of F2. And we can find alpha, beta, and gamma using our coordinate direction angle. So we know that alpha is equal to the inverse cosine of the x component of our force 2. So that's equal to minus 150 radical 2 divided newtons divided by the overall magnitude, which is equal to 700 newtons. So that's so again, this is just equal to cosine of F2x divided by the magnitude of F2 here. All right, and that's going to be equal to 108 degrees. All right, and then we can do the same for beta. It would be equal to the inverse cosine of the y component, which is 650 newtons, divided by 700 newtons, and that would give us about 21.8 degrees. And then we could do the same thing for gamma, which we would take the inverse cosine of the z component of force 2, which is 150 newtons, and divide by the overall magnitude, which is 700 newtons. All right, and we did that, we would get 77.6 degrees. All right, so to recap what we did, all right, we first looked at our using the problem statement and the geometry that was given to us in the problem. We wrote out our algebraic equation here for our desired unknown, which was force 2. So then we knew we had to write, in order to subtract force 1 from force r, we needed to write both force 1 and force r in Cartesian form. So using the coordinate direction angles, we were able to solve for the x, y, and z components of force 1. Alright, and then using the problem statement, we were able to write the resultant force in its Cartesian form as well. We then were able to just subtract the components, the x, y, and z components of force 1 from the x, y, and z components of our resultant force. And then using the x, y, and z, the magnitudes of our x, y, and z components, we could then square each of them and take the square root of it to determine the magnitude. And once we had the magnitude, we could then divide both the x, the y, and the z components by that magnitude and take the inverse cosines of each of those values to get our alpha, beta, and gamma terms, or the angle between the x, y, and the z axis respectively with our force 2 vector. All right, and that concludes this summary of how to subtract two Cartesian vectors and determine the magnitude of that final vector that we solved for and its direction.